Hello everyone. So this is part 2 of lecture 4, spread spectrum techniques, and in this lecture we are going to talk about pseudo-random codes and how they are used in spread spectrum. And these are the books I followed for preparing this lecture, so you can go through them if you want. So let us start. First of all, let us understand what pseudo-random or pseudo-noise sequences are. So in the previous lecture, we discussed a lot about different types of spread spectrum techniques, and there we used some kind of spreading sequence, right? Which are just a sequence of binary digits. Now, in spread spectrum, we saw that we have to first spread the signal. That means multiplying our input data with a much higher data rate signal, which is the spreading sequence, which is done at the transmitter. And at the receiver, we again despread the signal by multiplying again with the same signal, same spreading sequence, right? So this is the spreading and despreading process in spread spectrum. Now ideally this spreading sequence we are using, that should be a random sequence, so that the resulting sequence seems like a noise signal to other users, other unintended listeners, right? And for doing that, we should ideally use a truly random sequence. But if you do that, what will happen? The problem is that this signal, the spreading sequence we are generating at the transmitter, that should be generated at the receiver also, the same sequence. And if this is a random sequence, obviously at the receiver we cannot generate the same signal. That's why we should have some kind of solution for that. Our spreading sequence should have the characteristics or property of random signals, but it should not be random, it should be deterministic, so that we can generate the same signal at the transmitter than at the receiver also, right? So how can we do that? What is the solution for that? The answer is pseudo random numbers or pseudo noise sequence, as we will see in this lecture. Now, what is pseudo-noise sequence? Pseudo-noise sequence is a type of signal that appears to be random. That means it has the statistical properties of random signal, but actually it's not random at all. It is deterministic and periodic signal that can be generated at the transmitter, and using some initial knowledge we can generate the same signal at the receiver also. So now these PN sequences are generated using some kind of algorithm, and for that algorithm we have some initial value called seed. So even though this algorithm is deterministic, but it has some property that the resulting sequence we are generating from this PN sequence generator, that will pass different tests of randomness. So we have some kind of tests for checking whether a sequence is random or not. So we will see that later on. So this kind of sequences generated by PN sequence generator actually pass those tests. As a result, we can say that these sequences actually behaves like a random signal. That's why we have this name pseudo-random sequence. So it appears random, but actually it's not a random signal, it's pseudo-random sequence. So one last thing to add here is that let's say you want to generate particular PN sequence. If you don't know the algorithm and also the initial value for generating that sequence, obviously you can never generate the same sequence at the receiver. That's why the transmitter has to share that information, the algorithm and also the initial value called seed, to the receiver, so that the receiver can retrieve that data using that pseudo-random sequence. Okay, now randomness properties. As we discussed earlier, for a signal to appear like a random signal, it has to fulfill some properties. These properties are called randomness properties. So we have three properties like this, and if a signal fulfills these properties, we can say the signal has statistical properties of a random signal. These three properties are balance property, run property, and then correlation property. Now in the next section we are going to understand how these properties are actually defined, and also we are going to take one example sequence like this. So we have 15-bit example sequence. This is actually a pseudo-random sequence which we will generate later on, and for now we are going to use this sequence to test these three properties, and finally we will prove that our 15-bit sequence here is a pseudo-random sequence, right? So let us start with this. So first of all, let us start with property 1, balance property. So in this property, all we are saying that for our sequence here, the number of binary ones should differ from binary zeros by at most 1 digit. So if you look at this sequence, you can see number of zeros is 1, 2, 3, 4, 5, 6, 7. So we have 7 binary zeros, and for ones 1, 2, 3, 4, 5, 6, 7, 8, and we have 8 binary ones. So number of ones differ from number of zeros by 1. So our sequence here fulfills the property of balance. Now the next property is run. Now here run is defined as the sequence of consecutive bits of the same value, like a sequence of all ones or sequence of all zeros. This can be called as run. Like here, if you look at this one, for this sequence we have consecutive zeros, 3 zeros like this, then 1 starts. So this here is a run and this here is a run, and actually always we calculate the length of a run. Like here we have 3 zeros together, so for this run the value or the length of that run is 3. For this one the length is 1, length is 2, like this way. Now for this property, run property, it is desirable that from all the runs we can get from this sequence, 1/2 of those runs should be of length 1 and 1/4 of those runs should be of length 2, 1/8 of those runs should be of length 3, and so on. Like for example, we can also say 1/16 of those runs should be of length 4, or we can just generalize like this: 1 divided by 2 to the power nth of those runs should be of length n, right? So we will see this example how this is fulfilled for this sequence here. Now if you want to understand why this property is used for checking randomness, you have to understand that longer runs are obviously less likely to occur in truly random sequence, right? That's why we have this property. Now let us check this property for this sequence, the example sequence of 15 bits, right? So for this 15-bit example sequence, we have total number of runs as 8 runs, right? So if you look at this, this is one run of length 3, this is another run of length 1, this is another one of length 2, right? So in this way we have total 1, 2, 3, 4, 5, 6, 7, 8 runs, and from those 8 runs, how many of them are actually of length 1? This one, 1, 2, 3, 4. So we have 4 runs of length 1, which is half of 8 runs, the total number of runs. That's why we can say half of the total runs are of length 1. Now let us look at runs of length 2. So we have 2 lengths like this one, this run and this run. So we have 2 runs of length 2. 2 runs means compared to 8 runs, this is 1/4 of the total runs. So 1/4 of the total runs are of length 2. And we can check the same thing for length of 3. So we have only 1 run for length 3. That means 1 run, which is 1/8 of the total runs, and this is actually fulfilling all those properties, right? For the run property, it is fulfilling. Now we can do the same thing for runs of length 4 also, but what will happen, you know that for the runs of length 4, 1/16 of total runs should be of length 4. Now for this case, 1/16 of the total runs means 1/16 multiplied by total runs 8, which is half. So half is not an integer value, that's why we cannot calculate that. That's why we can stop at length 3. So we can say this sequence almost fulfills the properties of run. Now let us look at the third property, correlation. For this property, what basically we should maintain is that our sequence should not exhibit any kind of correlation between its different parts. That means using some portions of our sequence, we cannot predict another portions of the sequence. That is the correlation property we are seeking here. And for checking that property, what we can do, we can just calculate the autocorrelation function of our sequence. Autocorrelation means measuring the correlation between our sequence and a delayed version of itself. And if a sequence has high autocorrelation, what that means is basically our sequence has some kind of predictable pattern, and using that predictable pattern, unintended user can actually generate the same sequence, which we obviously don't want. Okay, that's why our random sequence should exhibit a very low autocorrelation. Now first of all, let us define autocorrelation function for a signal x of n, which has a length of n. That can be defined like this. So r of tau is the autocorrelation function for x of n, and here we can see that x of n is just multiplied with a delayed version of itself, and the delay value is tau, and for each tau we are going to get one value of r of tau. What we are doing here is basically we are just measuring the correlation between our sequence x of n and the delayed version of itself with delay tau. And here we are desiring a low autocorrelation value for our property. That means this r of tau should exhibit a very low value for all tau, except for the case tau is equal to 0, because if you take tau is equal to 0, then we are just multiplying x of n with itself, which should exhibit the maximum value possible for r of tau always. And for all the other cases, for all other tau, this should exhibit a very low value, and that is what we are calling as low autocorrelation for x of n. Now as always, we are going to test our example sequence of 15 bits for this property. And for our sequence, we can write or rewrite our autocorrelation function as this. So we have to change n as 15 because the length or the period of our example sequence is 15. Now some things has to be kept in mind for our case, like the shift parameter tau here refers to cyclic shift. For example, let's say if we have a sequence of 5 bits like this, 1 0 1 1 0, then cyclic shift by 1 bit means we're going to do something like this. We are doing right shift, that's why it will shift to the right 0 1 1 1, and then the last bit here, this will shift here. In this way it will shift in a cycle, right? That is referring to the cyclic shift. Now the next thing to keep in mind is that to get the correct autocorrelation result, we have to change our binary sequence to a bipolar representation. Like here, this was our binary sequence of 15 bits, right? We have to represent that using a bipolar representation. That means all the zeros should be represented with -1 and ones should be represented with +1 or 1. This is because we are calculating the autocorrelation function and there is a multiplication, and when you are multiplying with 0, that actually results nothing. That's why to avoid that, we are using the bipolar representation. Now we are going to calculate the value of r of tau for this example sequence. So what actually we have to do here is we have to calculate the value for each tau. Tau is equal to 0, tau is equal to 1. Then finally, by accumulating all of these values, we are going to get the final function r of tau. Now if we remember, our autocorrelation function for this example sequence was something like this. R of tau is equal to 1 divided by 15, which is the period, and n is equal to 1 up to 15, then we are multiplying this two portion x of n with a delayed version of itself, right? So now for tau is equal to 0, what will happen? We have to first of all have to take our sequence x of n, right? And as we know, for tau is equal to 0 there is no shift, so x of n minus 0 is exactly the same sequence. And finally we have to multiply all of them, right? So we are multiplying in this way. So minus 1 multiplied with minus 1, which is plus 1, minus 1 multiplied with minus 1, which is plus 1. So in this way all of these values are multiplied, and finally these bits should be added up to get the whole summation here, right? So that value comes as 15, right? So then we can calculate that as 15 multiplied with 1 divided by 15. So this 1 divided by 15 is here, and after calculating the whole summation here we are getting 15. So the resultant comes as 1. So r of 0 is equal to 1. In the similar way we can calculate for tau is equal to 1. So for tau is equal to 1, we have the example sequence x of n here. Then we have to take a shifted version of itself with tau is equal to 1. So that means this is a cyclic shift. So all of these values should be going here like this, shifted to the right by 1. And finally you see this value here, this is going here. So right shifted by 1. And then finally we have to multiply these two values. So minus 1 multiplied with plus 1 is equal to minus 1. Minus 1 multiplied with minus 1 is equal to plus 1. So in this way all these values are calculated. Finally this sequence here, these 15 bits are added together, and which comes as minus 1, because if you look at that we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 minus 1s, and 1, 2, 3, 4, 5, 6, 7. So 7 plus 1, 8 minus 1, which results in minus 1 value. So then finally we have to multiply that with our period 1 divided by 15. That comes out as minus 1 divided by 15. So r of 1 is equal to minus 1 divided by 15. In the similar way we have to calculate for tau is equal to 2. So this value is just right shifted by 2, and finally we get the value as minus 1 again, and r of 2 is equal to minus 1 divided by 15. Exactly in the similar way for tau is equal to 3 also we are going to get the value as minus 1 divided by 15. So we see some kind of pattern here, right? So that pattern can be explained after calculating all the values for all taus. That comes out as r of t is equal to 1 for tau is equal to 0, 15, 30 like this, and otherwise it will have a very low value of minus 1 divided by 15. And graphically this is how we are going to represent our r of tau. So you see here, when we have tau is equal to 0, at that moment we have the maximum value for r of tau, and for all the other cases we have a very low value. After completing one sequence, again we have the maximum value of autocorrelation. Now these values here, how to interpret those? To understand that, we can say that for a correlation value of 1, the second sequence exactly matches with the first sequence, and when we have a correlation value of 0, that means there is no relation between the two sequences. And when we have a value of minus 1, that means these two sequences are exact mirror images of each other. That means minus 1 also denotes some kind of correlation, but in the reverse order. Now for our case, for our sequence, r of t has the maximum value of 1 when tau is equal to 0, and otherwise we have a very low value of minus 1 divided by 15. So therefore we can say that our sequence has a very low autocorrelation and fulfills the third condition for randomness. And generally for a PN sequence of period n, this is expected to have similar kind of autocorrelation function. That is, for tau is equal to 0, n to n like this, it should give a value of 1, and otherwise it should give a value of 1 divided by n. And in this way, if a sequence fulfills all these three properties of randomness, then we can say that this is a random sequence, or at least have the statistical properties of a random sequence, and that can be used for spread spectrum. So far we have discussed about the properties of a random signal, and now we are going to see how these pseudo-noise or pseudo-random sequences are generated. Now the circuit we use to generate these kind of sequences are called linear feedback shift register, or simply LFSR. This circuit consists of some XOR gates and also a shift register. Now to understand how these LFSRs work, let us start with a basic example of 4-bit LFSR. So this is that example of a 4-bit LFSR, and here we can see this has a 4-stage shift register and a XOR gate, right? So this XOR gate is taking some input here and taking that as feedback to B3. Now this for this shift register here, B3, B2, B1 and B0 are the corresponding stages, and each of these stages has the ability to store 1-bit data. And obviously there will be some clock pulses which will govern this whole circuit, which is not shown here, and at each clock pulse contents of each stage will be shifted to the right. And also at the same clock pulse, what will happen, the contents of B1 and B2 will be XORed together and the output will be fed back to B3. Now the contents of B0 will be taken as the output for this circuit, the output of this LFSR. So that means at each clock pulse we are going to get 1-bit output as result, which we will get from B0. And sequentially after each clock pulse we are going to get 1 bit of our desired PN sequence. So after some clock pulse we will have a sequence of digits called as PN sequence. Now that we understand the architecture of this 4-bit LFSR, let us try to observe how it actually operates. Now initially we have to store some value in our shift register, and that value is called seed. For our case, that initial value will be 1 0 0 0. So we are going to store 1 in B3, B2 will be equal to 0, B1 equal to 0, and B0 will be equal to 0. So this is the value we are going to store, which will be our initial state for our LFSR. Now from this table, let us try to understand how in each clock pulse the contents of each stages of the register is changing, and as a result the output will also change, right? So also, if you remember, we have a XOR gate here as feedback. So at each clock pulse the contents of B1 and B0 will be going to this XOR gate as input, and the output will be going to B3 as feedback, right? So let us try to remember what the outputs of a XOR gate should look like, right? A very easy way to remember that is, if we have odd numbers of 1 at the input for a XOR gate, then the output should be 1, right? So let's say, for example, we have 4 inputs for a XOR gate. If we have odd numbers of 1 as input, then obviously the output will be 1. So that means this formula can be applied for any XOR gate with any numbers of input. And we have only 2 inputs here for this XOR gate, so it will be very easy to apply this formula. Now let us look at the initial state. So initially we had the value 1 0 0 0 stored in our shift register, and B1 and B0 will be going to this XOR gate, and the output should be 0 because there are 0 binary ones here, so result is 0. And at the next clock pulse, what will happen, the contents of this result will be going to our B3 stage, right, like this. And obviously all the contents of each stage will move to its right stage, right, like this. So like this it will move to its right stage. And in the previous stage, if you remember, B0 will be the output, so that's why B0 is taken here as output for initial state. And for the next state, state 1, B0 is 0, so that will be taken as output here. And again we can do the same thing, that means B0 and B1 will be going to our XOR gate, and the result will be again 0, and that value will go to B3 in the next state, like this. And again all the contents will be going to its right stage, like this. Okay, now here again B0 is 0, that value will go here. And now we have two values, 1 and 0, which will be XORed together, right, to get the result 1, because we have one binary 1 here, odd numbers of 1s are there, so output will be 1, and this value will go to our B3 in the next state, and all the values will be going to its right position, like this. And B0 is 1 right now, so that value will be going here, like this. So in this way we have to find out the value for each clock pulse. And if we keep doing that, we will see that when we reach state 15, we will have the exact same 4-bit sequence we used as our initial state. So 1 0 0 0 is again coming out here. So that means we should stop here at state 14. So starting from 0 up to 14, we have 15-bit sequence. So the length of our PN sequence is 15, or we can say the period of our sequence is 15, and that sequence is this one. So 0 0 0 1 0, like this. So this is our sequence. And if you look closely, you will see that this is the exact same sequence we used for testing the randomness properties. So this sequence actually fulfills those 3 properties, and we can say this is a pseudo-random sequence. We can use this sequence as a spreading sequence in our spread spectrum. Now another thing to note here, for this 4-bit LFSR, if you start with a different initial value, then we are going to get the exact same sequence, but that will start with a different binary bit. So let's say if I start with this one, 1 1 1 0. So if I start with this 4-bit initial state, then our sequence will start from here, then maybe we will have a 15-bit sequence. So the same sequence is there, but it will start from a different bit. That's the only difference for this kind of 4-bit LFSR. Now let us talk about maximal length sequence, or M sequence. The interesting thing is, previously we had seen a 4-bit LFSR circuit, but this is not the only configuration possible for a 4-bit LFSR. Like for example, this is another possible configuration for a 4-bit LFSR, and we can see there is an extra XOR gate that will come as feedback to B3, right? And because of that extra feedback, we will have different results, as we are going to observe right now. Let us take initial state 1 0 0 1 for this 4-bit LFSR. Then using this table we can understand how in each clock pulse the values will change, right? So our initial state is 1 0 0 1, and we have to calculate the result of B0 XOR B1 XOR B3, right? Because we have 2 XOR gates here. So here B1 and B0 are going to this XOR gate. That result will go here, and B3 will be coming here. That means the whole result is B0 XOR B1 XOR B3, right? And we know if for a XOR gate there are odd numbers of binary 1 as input, then the output should be 1, right? So you can calculate here B3, B1 and B0 are the inputs for this XOR gate, right? So the result should be 0 because there are 2 binary 1s, even numbers of 1, right? And that value, it will go to B3 as feedback, right, in the next clock pulse, and all the values of each stages will go to its right stage like this, just like before, right? Then again we have to take B3, B1 and B0 and have to XOR it together, and we have 3 zeros, so the result will be 0. That value will go to B3 in the next state. All the values will go to its right stage like this, and for each of the cases we can take the output from B0, right? So B0 is going there. So in this way we are going to get a 3-bit sequence actually. Okay, after that when we have state 3 we will see that we are again finding out the same 4-bit sequence we used as our initial state. So the period of our generated sequence is 3, which is quite shorter compared to the previous case, right? In this way, based on the number of stages we have for our LFSR, number of feedbacks we have, and also the initial state we are using for our LFSR, based on that the pattern and the period of our generated sequence can change, right? Now the sequences, sequences we are generating from these LFSRs, they can be classified as either maximal length or non-maximal length. And here the maximal length sequences, which is also called M sequences, this kind of sequences have the property that for an n-bit LFSR, the generated sequence will have the period as 2 to the power n minus 1, which is the longest possible period for an LFSR with n stage. Okay, that's why it's called maximal length sequence. And if the sequence length is less than that, then we are going to call that non-maximal length sequence. For example, if we look at the first example of our 4-bit LFSR, there we had n is equal to 4. Number of bits for our shift register was 4, and the period of our resultant sequence or generated sequence was 15, which is 2 to the power 4 minus 1. So this sequence actually fulfills our 2 to the power n minus 1 condition. That's why we can say this is a maximal length sequence or M sequence. Okay. Now for the next example, for the second one, we had a 4-bit LFSR again, but for that we had 2 XOR gates as feedback, and there the resultant sequence had a period of 3, which is less than that value. Okay, that's why that generated sequence is a non-maximal length sequence. Now why this maximal length sequence or M sequences are important for our spread spectrum? This is because the longer the duration or period of our sequence, the better. It will be harder to detect, harder to predict, obviously, and also the autocorrelation property of M sequences are better than those which are non-maximal. Okay, that's why we always try to generate sequences that are maximal. M sequence should be generated for our spread spectrum. So far I think we have a very good understanding of how an LFSR works. So now let us try to develop a generalized definition for an LFSR. So let's say we want to develop an n-bit linear feedback shift register like shown here, right? So obviously that LFSR will have a shift register with n stages, right? And each stage will have the ability to store 1-bit data like here shown. Okay, and our LFSR can have several XOR gates, and the number of gates can vary starting from 1 up to n minus 1. So you see these are the XOR gates we have here, and the number of them can vary starting from 1 up to n minus 1. And presence or absence of a XOR gate can be represented by multiplication with AI, which has 2 possible values, 1 or 0. So you see in this figure we have AI values A0, A1, like this. Okay, so as AI has the possible value of 1 or 0, that means whenever we have one value, this circuit is totally completed. Okay, so whatever value we have at B1 will be sent to our XOR gate for feedback, right? And if A1 is equal to 0, then this circuit is disconnected. There will be no connection from B1 to this XOR gate. So in this way, we can understand the function of our multiplication with AI. In reality, actually, we don't have this kind of multiply circuits. Basically, AI is equal to 0 means there is no connection here, and AI is equal to 1 means there is some connection for feedback. Okay, so in this way we can have different amount of connection here possible, starting from 1 up to n-1 connection, and that will lead up to the feedbacks we are talking about from XOR gates, right? Now actually we can think of our LFSR as the implementation of sum of XOR terms. So because you see these two are getting summed up in this XOR, and finally like this all of them are getting feedback to Bn. So Bn is equal to A0, B0, XORed with A1, B1, XORed with like this. So this formula is actually being represented by our circuit, right? So this is our n-bit linear feedback shift register. So now we have reached the final portion of our lecture. So as we understand everything about spread spectrum, now we can discuss what are the benefits of spread spectrum and how they actually work, how they are actually helping us in communication systems. So in previous lecture also we briefly talked about what are the benefits we are getting from spread spectrum, like it can offer resistance from jamming, and also from interference we can reduce the amount of interference we are getting from communication system or the channel, and also we can minimize the effect of multipath fading. And finally we talked about CDMA, or code diffusion for multiple access, which is just a variant of spread spectrum commonly used in our mobile communication systems. So in the previous lecture we just briefly talked about these benefits, but we still don't know how these kind of benefits are offered by spread spectrum, how actually these things are implemented, right? So the first three benefits, these things will be discussed in this lecture, and in the next lecture we will understand how code division for multiple access is actually implemented. So in this lecture we are going to understand in detail some of the things spread spectrum offers and how they are implemented. So let us start with that. First let us start with jamming resistance capability of spread spectrum. So in the last lecture also we discussed about spread spectrum and said that these kind of techniques were initially developed for military applications, right, to avoid jamming. So what is jamming? Signal jamming means when we want to block or disrupt some signal by broadcasting a noise signal at the same frequency of the targeted signal, right? For example, in figure A, if you want to understand that, the sync function we are seeing here, this is the targeted signal we want to jam. For that, what we do, we take the same frequency band of that targeted signal, which is B, and we broadcast a noise signal like this. And as a result, obviously, at the receiver side, receiver cannot distinguish between the actual signal and the noise. Now let us try to inspect the first scenario here. So in this graph, we are seeing the power spectral density of these two signals. And power spectral density means how power is distributed over different frequencies. That thing is shown here. And if I calculate the area under this curve, the rectangle, then we are going to find out the total amount of power for our jamming signal, which is P. And our jamming signal covers the whole bandwidth B, just same as our targeted signal. And as a result, the value of power spectral density for the jamming signal is J0, right? which is P divided by B, total amount of power divided by the bandwidth cover. So the value of J naught, this is quite high, and as a result it will successfully jam our targeted signal for this scenario. Now what will happen if our targeted signal is transmitted using spread spectrum technique? That kind of scenario can be observed in figure B and figure C, where the targeted signal is being transmitted using some kind of spread spectrum techniques, and as a result it is occupying a much larger bandwidth of Bs compared to the previous bandwidth B. Now what can we do to jam this signal? And we have to also assume that we are using the same amount of power P just like before to jam this new signal which covers the bandwidth of Bs. Now for this case, the jammer has two possibilities if he has to use the same amount of power P. Either he can cover the whole bandwidth of Bs, then obviously the value of PSD should decrease, which is J1. J1 should be equal to P divided by Bs, as the value of Bs is quite high compared to before. As a result, the value of J1 will be much less. And the second choice the jammer can take is that he can keep the same amount of PSD of J0 just like the first case, but then the amount of bandwidth he can cover is constrained to B. So he cannot cover the whole amount of bandwidth Bs. In both the scenarios, the jammer will basically fail to properly jam the signal, because for the first case J1 is not high enough to jam the signal. As a result, the receiver will detect the signal he wants to receive. And for choice 2, the jamming signal can cover only some portions of our whole bandwidth. As a result, some signals will be received at the receiver. So in this way, using spread spectrum, we can mitigate or minimize the effect of jamming. Okay, next we are going to discuss about the interference rejection capability of spread spectrum. Now to understand this process, we are going to take this scenario as example. And this is just a typical DSSS system with x of t as input, just like before. But here, for the sake of simplicity, we are omitting some of the portions, like we don't have any digital modulation or demodulation part here, so we are not going to multiply with cos 2 pi fct here. And we know for this case, obviously x of t will be multiplied with our PN sequence or the spreading sequence C of t, and the resultant sequence is S of t. And then we don't have any kind of digital modulation, so that S of t will be transmitted to our channel. Now previously when we discussed about DSSS system, we took the ideal case. That means there was no noise or interference in our channel, right? But here we are saying that the transmitted signal will be added with some interference I of t, and that resultant signal will be received by our receiver. So we are saying the signal received at our receiver is R of t, which is S of t added with I of t. Now we can expand this signal R of t as this one, because we know S of t can be written as x of t multiplied with C of t, because S of t is the resultant signal after x of t gets multiplied with C of t. Now at the receiver, we know that the received signal will be multiplied with the same exact PN sequence C of t, right? So that process is there. So we are multiplying with C of t to get the output signal here, right? Let us expand that expression. So we are just taking R of t here. So x of t C of t plus I of t is R of t, that is written here. Let us try to expand it even more. So we have final expression like this. So CFT, we are just multiplying with this portion. And now if you look at this expression, you will see that previously, from our previous understanding, we know that C of t multiplied with itself will result in a value of 1. So this portion can be written as 1, and the final output signal can be written as x of t plus I of t C of t. because C of t multiplied with C of t is equal to 1. So this is our final output signal. We have x of t but some interference portion. And let us try to examine this scenario in frequency domain. So what will happen? We know that the signal we want to transmit, x of t, that gets multiplied twice because it gets multiplied at the transmitter once, then again at the receiver it gets multiplied again. But for the interference signal, it will get multiplied only one, because if you look at this one, our figure here, so x of t will get multiplied here with c of t and again here also. So twice x of t gets multiplied twice, but the interference is initialized here, so it will get multiplied only once, right? As a result, what will happen? At the receiver, we are going to get back our signal x of t, but there will be some interference term I of t multiplied with c of t. This is because our input signal x of t will get multiplied twice, once at the transmitter, that will spread our signal, and at the receiver it will get disparate, and finally we are going to get x of t, the original bandwidth of x of t will be retrieved. But for the case of interference I of t, it will get multiplied only once with our spreading sequence c of t, and as a result our I of t will get spread. It will just get spread only, and it will increase in bandwidth and decrease in power. That can be shown graphically in the frequency domain like this. So this blue signal is our input signal x of t with original bandwidth shown here. After the spreading process, what will happen? Our input signal will have a much broader spectrum, but at this channel, this interference I of t will be added with this one, with this amount of bandwidth. The orange curve is the interference, and at the receiver the combined signal will get multiplied with our spreading sequence again. As a result, our input signal x of t will get disparate, so we are going to get back our original bandwidth. But for interference I of t, what will happen? As it is multiplied with c of t only once, the bandwidth of our I of t will get expanded, and that's why we are seeing the orange curve got expanded with increase in bandwidth but decrease in power. And now if I just apply a low pass filter centered at this frequency to retrieve our signal x of t, then all the interference portions will be eliminated, and we are going to get back our original signal x of t, right? So in this way we can actually reject interference using spread spectrum. And the basic idea here behind interference rejection capability of our spread spectrum is that the intended signal x of t here is getting multiplied twice. As a result, it will get spread at the transmitter, and at the receiver it will get multiplied again, and that will disparate our signal, and finally we are going to get back the original bandwidth of our signal x of t. But for the case of interference here, interference will get multiplied only once, and as a result the bandwidth of our interference signal will get expanded, so amplitude will decrease, and as a result it will be very easy to distinguish between x of t and I of t. Okay, the last one is minimization of fading effect in spread spectrum, and to understand that we have to consider a DSSS system which is operating over a multipath channel, right? And as an example we are taking this case here. So we have two discrete paths in the channel, multipaths, and one of them is the line of sight direct path with 0 delay, and another one is non line of sight path with delay tau. Now we have to somehow transmit the signal x of t using this multipath channel to our receiver, right? And for the sake of simplicity, here also we are omitting some of the portions just like the previous case. So we are omitting the digital modulation and demodulation portion here. So we are not going to multiply with cos 2 pi fct. And we know that for this DSSS system, what will happen at first, x of t will get multiplied with our PN sequence c of t, and the resultant sequence is s of t. And as there is no digital modulator here, s of t will be transmitted using our transmitter, right? And as we have two paths here, two multipaths in our channel, so two versions of this s of t will be received at the receiver. One of them is the s of t from this direct line of sight path, and another one is from this path, non-line of sight path with delay tau. So that version or that component is st minus tau, right? So two versions of s of t will be received at the receiver. So finally we can say the received signal r of t is s of t plus s of t minus tau, and we can expand this expression as x of t multiplied with c of t. Same goes for this one also, right? So this is our final received signal. Now at the receiver, what will happen? At the receiver, r of t will be correlated with our spreading sequence c of t. So what is correlation here? This correlation basically is kind of like our inner product, like we described in OFDM lecture. So first of all, this received signal r of t will be multiplied with c of t, and for a symbol duration t, all the results will be integrated. So if you want to be accurate, you should have some kind of integrator module here, that is integrating over a symbol duration like this. And most of the time in the textbook you will see that this term is written as correlation, even though it is kind of like inner product. So that should be done here. And now mathematically we can represent output signal as this one, as r of t will be multiplied with c of t first, then the result will be integrated over a symbol duration t. So that is done here. We can just put the value of r of t here, which is this one, and expand the expression like this, and we can take two integrations. So we can just separate these two portions with two different integration. This is our final output signal, right? Now for this output signal, what we can understand here is that x of t and also x of t minus tau, these values are actually a fixed value for the whole symbol duration t, right? Because these are the signals we are transmitting. For a symbol duration, x of t and x of t minus tau should be fixed, or it should not change with respect to time. Therefore, they can be assumed as constant and can be kept outside this integration. So that is done here. We can take this x outside, and also for this term we are calling this x tau, and that is kept outside of our integration. Now we have to somehow calculate these two integrations, and to simplify these portions we can use the properties of correlation of PN sequence c of t. We know that c of t multiplied with c of t results in 1, so this value should be 1, and so this integration should result in a value of t. And we know that when we have c of t multiplied with a delayed version of itself, that delay is tau, right? From that autocorrelation property, for a PN sequence, when it is multiplied with a delayed version of itself, it will result in a very low value, like our third case, right? Correlation property of randomness. From that property we can say that this integration here will result in a very low value, almost equal to 0. So we can use these two properties here in these two integrations. So here this should result in t, and this should result in a value which is very close to 0, or we can just assume as 0, right? Now these assumptions here, that can be done only if path delay tau is greater than chip duration tc. This is because when we have tau is less than T of C, then C of T is almost equal to C of T minus tau, because this value is very small, so that they are almost the equal sequence. So obviously we cannot make this second assumption here if this condition is not true, right? That's why this condition has to be true for making this assumption. So finally, by using this assumption, we can get our final output signal, which is x multiplied with t, and this portion will be omitted, and finally we are getting this result. This is just x of t multiplied with a scaling factor. So finally we are getting our input signal x of t coming from direct line of sight path, and the non line of sight component here is omitted, right? Okay, so using this process we can actually omit or reject any components coming from different path delays in a multipath environment. This is the basic process of minimization for multipath fading effect used in spread spectrum. Finally, frequency hopping spread spectrum can also minimize or mitigate this effect of multipath fading, but how they do is quite different from the process we have just seen here. So for FHSS, what they do is, we know for FHSS we will have different frequency bands available, right, for hopping. Like I can draw it here like this. So maybe this is F1, this is F2, this is F3. In this way, maybe this is F of n. So for FHSS, we basically just hop from frequency to frequency with respect to time. Now here the change of frequency will be very rapid, and as a result, before the delayed version or multipath component of a signal can arrive, we are already going to change the receiver band position, and as a result we are going to avoid or minimize the interference of fading. So this is the basic process of FHSS for mitigating the effect of multipath fading. That's all for this lecture. Thank you.